Hello guys. In this video, we are going to define the variance. Most of you must have heard about the variance before, somewhere else in other statistics course, or in your daily life, you hear about this often or not. I don't know. Anyhow, it's very famous. But we have to restart the definition. Let's start from the very fundamental uh, idea. We are defining a measure of variability. And as we learned before, as I explained before, it is about the deviation from the center. So the measure of a measure of the central location captures where the center is, and we are looking for information not contained in this measure. So that is about the deviation, how much observations are away from the center. That is the main idea. And from now on, we are there can be many possible candidates for the center, but we are going to use the mean, expected value of x, random variable x, as the center. We are not going to question that. It's reasonably popular, mean is reasonably popular as the center, so it's not a problem at all. And then once you define the center, a deviation is easy to be defined. A deviation of the ith ith observation is the difference. Observation from difference from the mean, right? So it's a simple way to define a deviation. Now let's think about numerical example. I will continue from the weather example about Honolulu. And simply, we could consider more complicated data set, but let's simply consider 4 numbers by each season, and I simplify those numbers. Simply assume that in spring, the average temperature is 76, in summer 82, in fall 80, winter 74 degrees in Fahrenheit. And then if you take these 4 numbers as a data set, then you can calculate the mean. It's easy. The average of these 4 numbers equals 78. So it's very easy to calculate. And then it means the center is 78. From the center, you can define the deviations for each observation. The first observation is 76, so its deviation is minus 2 because it's 2 degrees below the average. And in summer, the temperature is 4 degrees above the average, so the deviation is plus 4. And in fall, plus 2, in winter, minus 4. So what you are doing here is you are subtracting the mean from each of the observations, right? And you get deviations as many as the original observations. So you get, because you had 4 observations, you get 4 deviations. If you had more observations, you are going to get more deviations. And after you calculate the deviation, the problem of the deviation is that some of them are negative, but distance cannot be negative, but we want the distance from the center. That's what we are interested in. We are looking for distance. And also we know that summer plus 4 and winter minus 4 are equally distant from the center, right? It does not matter where you deviate. It could be positive, it could be negative. Anyhow, what matters is the center. So we would like to remove the negative sign, and one simple way to do that is by taking squares. We are not interested in the sign, but only in the magnitude. And if you take squares, all the negative numbers become positive. So we define square deviation as deviation squared, right? Inside those parentheses is deviation and then squared. So we make another random variable, square deviation. Minus 2 squared is 4, plus 2 squared is also 4. So minus 2 and plus 2 has the same distance. And plus 4 squared is 16, minus 4 squared is 16. So those two are also at the same distance. However, the plus 4 is further away from the center than minus 2 is. So the square deviation for summer is greater than that of spring, right? So literally, you may think square deviation as the distance because the further from center, the larger the square deviation is, and it is always positive. Or if you are exactly at the center, the square deviation will be 0. So it it is a distance. It's some in the unit of squared deviation. And also you get squared deviations as many as the original observations, right? So you can consider the squared deviations as a new random variable. The next step is now just take the squared deviations as a new random variable. I don't need the other numbers now. I only take the squared deviations. It is a new data set. You may treat it as a new data set. And what we are doing here is we are going to calculate the mean of these squared deviations. The variance is the mean of the squared deviations. This is the definition. And we defined the mean in the previous chapter. So if you're curious what is the mean, watch the videos. And again, the larger the variance is, the more volatile. So the larger the variance is, the greater distance, the observations are at further distance, so they are more volatile, more spread out. And it is always non-negative because everything was squared and usually denoted as variance of a random variable x or Greek letter sigma squared or s squared. So there are many ways, many different notations depending on the context. But one thing that I don't like about the variance is this terms. From the very beginning of this course, this semester, I defined population and sample in this way. I said the population is conceptually when you have an infinite number of sample size, but the sample is a finite sample size, so it's the easiest way to understand the difference between the population and the sample. However, so you may define population variance and sample variance according to the same notion, but these names are taken by formulas. That's very frustrating. I don't like them. The population variance formula is defined in this way. So look at this. This is inside the parenthesis is deviation, and take square, so square deviations, and you sum the square deviations, and you divide the sum by the sample size. So summation and division by sample size is how you calculate the average, right? And we call this the population variance formula, and Excel function is variance.var.p. If you use this function in Excel, then Excel will calculate this. But annoyingly, there is another variance formula, which is called the sample variance formula, and strangely, it uses n-1 in the denominator. You sum all the square deviations, and you have to divide it by the sample size to calculate the average of that. But you are taking n minus 1. You are dividing it by n minus 1 instead of n. So this is the sample variance formula. The details why we are using this, that is explained in a later chapter. So, but in this chapter, what I can say is there are two different formulas, and in the homework, I will tell you which formula you have to use. And actually, sample variance formula is more common. It's very sad. I don't like that, but that's the reality. So, and so back to the example, numerical example, we had 4 squared deviations. So we treat them as new random variable. And if you calculate the population variance, it is sum of these 4 numbers divided by sample size 4. So simply it's 10. But if you use the sample variance formula, summation is the same, but you divide it by the sample size minus 1. So the sample variance becomes 13.33. Oh, I don't know why I wrote 4. It's not 4. 13.33 is the sample variance. So something is not going well. So it's different, obviously different. And surprisingly, the sample variance formula is more commonly used. You are going to learn why in chapter 8. Just very brief intuition is that we are doing n minus 1. So if the sample size is 1, you cannot calculate the variance, right? And the formula does not exist. It is also true because the variance is about distance. But to calculate the distance, you need at least 2 points. 2 observations is the minimum to calculate a distance. So in that sense, sample variance is not defined. Variance is not defined when you have only 1 observation. That is kind of an intuition, justification why you need to use n minus 1. Anyhow, more theoretical reason is explained in chapter 8. Look forward to that. To summarize, if you want to calculate the variance from raw data, you have to follow these steps. It's quite complicated. First, you have to calculate the mean. Calculating the mean itself includes several steps, but these were shown in the previous chapter, so let's make it one step. We need the mean because we have to fix the center, and then we are going to calculate the distance. So once you fix the center, you subtract the mean from each observation, so you obtain the deviation, which is the distance from the center, and then square each of the deviations to obtain square deviations, and you have as many square deviations as the sample size. Using them, we are calculating their average. So sum the square deviations and divide by the appropriate number for your formula. When you use the population variance formula, you have to use the sample size n. But if you use the sample variance formula, use n minus 1. By the way, when the sample size is small, like 4, it matters a lot. But when the sample size is large, like say 10,000, then what you're doing is the difference between 10,000 and 9,999 is quite small. So when sample size is large enough, the difference is quite minimal. But in our example, they are quite different. Okay, then now it's your turn. Try this. I calculated the mean temperature already for you, and using this, calculate the sample variance for Phoenix. the Honolulu variance was already calculated, so use the same procedure to calculate the sample variance for Phoenix. And please do the math and watch the next video after you finish your work. Thank you.